Bismillahirrahmanirrahim. Welcome to Applied Thermodynamics by McConkey with Dr. Abid Hussain. In this lecture, we are solving problem 4.19. So, problem statement is a turbine is supplied with steam at 40 bar and 400 degrees centigrade. So, first we write given data. Given data. So, initially pressure in turbine is 40 bar and temperature T1 is equal to 400 degrees centigrade, which expands through the turbine and steady flow to an exit pressure of 0.2 bar. After expansion in the turbine is used for work output, so in turbine there is expansion and pressure decreases. So pressure decreased from 40 bar to 0.2 bar, and the dryness fraction after expansion is x2 is equal to 0.93. The inlet velocity is negligible, c1. Inlet velocity is c1. c1 is equal to 0. But the steam leave at high velocity through a duct of 0.14 square meter. A2 is equal to 0.14. Cross section, if the mass flow is 3 kg per second, m dot mass flow is equal to 3 kg per second, and the mechanical efficiency is 90%. Efficiency mechanical is equal to 90%. Percent mean out of 100, so 90 divided by 100 is equal to 0.9. Calculate the power output of the turbine. Required is to calculate power output. Show the process is irreversible. Show that the process is irreversible, and calculate the change of specific entropy S2 minus S1, and heat loss from the turbine are negligible. If heat loss are negligible, it means that the process is adiabatic and K is equal to 0. So we start solution. So initially pressure is 40 bar and T1 is equal to 400 degrees centigrade, and secondly, even after expansion in a turbine, dryness fraction is 0.90. It means that after expansion the steam is in wet region, but we don't know about the initial condition. So first we check whether initial forms are in wet region or in superheated region. So from saturated steam table, at pressure is equal to 40 bar, saturation temperature is equal to 250.3 degrees centigrade, as T1 given to us as 400 degrees centigrade is greater than T1 is, which is 250.3 degrees centigrade. So initially steam is superheated, and I am showing this on TS diagram. This is 400 degrees centigrade. T1 is equal to 400. Temperature is in degree centigrade, and entropy is in kilojoule per kilogram per Kelvin. Initially steam is superheated. This is 0.1, and finally this is adiabatic process, constant entropy process, so this will be straight line, and finally 0.2. Here x2 is given to us. X2 is equal to 0.93. It means that Finally, the steam is in wet region. So this is TS diagram for the problem. So now we are find work, power and power output and change in entropy. So power output we will use steady flow equation. So from the steady state equation, Q dot plus W dot plus M dot into H1 plus C1 square divided by 2 is equal to M dot into H2 plus C2 square divided by 2. So Q is 0, so Q dot will also, if Q is 0, then rate of flow of heat will also be 0. We will find power output. This is power output. W dot, rate of flow of work, is power output. M dot is given to us. We can find H1 and H2 and C2. First we find for this formula H1, H2 and C2. And for entropy change S2, we will find S2 minus S1. So first we are finding H1, H2, S2, S1 and C2. So initially steam is superheated in superheated region. Initially steam is in superheated region. So from superheated steam table, at pressure is equal to 40 bar and temperature is equal to 400 degrees centigrade. H1 is equal to 3214 kilojoule per kg and S1 is equal to 6.769 kilojoule per kilogram per kilo. Now finally after expansion and turbine, the steam is in wet region. Steam is in wet region because x2 is given to us, because x2 is equal to 0.93 and dryness fraction is defined from 0 to 1 and wet region. So we will use formulas. H2 is equal to HF plus X Hg minus HM, and for S2 SF plus X Sg minus SF. So from saturated steam table, at pressure is equal to 0.2 bar, SF is equal to HF is equal to 251 kilojoule per kilogram and Hg is equal to 2609 kilojoule per kg and SF is equal to 0.832 kilojoule per kilogram per Kelvin and Sg is equal to 7.907 kilojoule per kilogram per Kelvin. Now we are finding H1. H1 is equal to HF plus XHG minus HF. The value of HF is 251 kilojoule per kilogram plus the value of X2 is 0.93 and Hg is 2609 kilojoule per kilogram minus SF is equal to 251 kilojoule. So this is very simple calculation. If we first subtract 251 from 2609, then multiply with 0.93 and then add 251. So the answer will be 2443.94 kilojoule per kilogram. And S1 is equal to SF plus X Sg minus SF. So SF is equal to 0.832 kilojoule per kilogram per Kelvin, plus the value of X2 is 0.93 and Sg is 7.907 kilojoule per kilogram per Kelvin, and SF is equal to 0.832 kilojoule per kilogram per Kelvin. Now this is also very simple calculation. Subtract 7907 minus 0.822, then multiply with 0.983 and then add 0.832. So the answer will be 7.411 kilojoule per kilogram per Kelvin. Now we are finding S2. So for S2 we are using continuity of mass equation. From continuity of mass equation, C2 is equal to m dot V2 divided by A2. M dot is given to us mass flow rate 3 kilogram per second. V2 is equal to, first we are finding V2. V2 is not given to us. First we are finding V2. So V2 is equal to XVG. So from saturated steam table at pressure is equal to 0.2 bar. Vg is equal to 7.648 meter cube per kg. So V2 is equal to X is 0.93 multiplied by 7.648 meter cube per kg. So V2 is equal to 7.11 meter cube per kg. Now we can easily find C2. So C2 is equal to M is 3 kilogram per second, V2 is 7.11 meter cube per kg, and A2 is equal to, which is given to us, 0.14 square meter. Now this is simple calculation. Calculate this and the final answer will be 152.3 meter per second. Now we are finding W dot, power output. So from steady flow equation, Q dot plus W dot plus M dot H1 plus C1 square divided by 2 is equal to M dot into H2 plus C2 square divided by 2. Here we know that there is no heat loss. Q is equal to 0. So Q dot will also be equal to 0. Initially velocity is negligible. So C1 is equal to 0. C1 square divided by 2 will also be equal to 0. So W dot is equal to M dot H2 plus C2 square divided by 2 over minus M dot into H1. So M dot is common in both. So M dot is equal to W dot is equal to M dot H2 minus H1 plus C2 square divided by 2. Now W dot is equal to, the value of M dot is 3 kilogram per second. The value of H2 is 2443 kilojoule per kilogram minus the value of H1 is equal to the value of H1 is equal to 3214 kilojoule per kilogram plus C2 square. The value of C2 is 152.3 meter per second whole square divided by 2. Here is a problem. This unit is kilojoule per kg, this unit is kilojoule per kg, and this is meter square per second here. Meter square per second square. So this is meter square per second square. Here it is clear to us that kilojoule per kg is equal to meter square per second. First I solve this unit, joule per kg. So joule per kg, joule is equal to Newton meter per kilogram. Newton is equal to kilogram meter per second square, and this meter, and this is kilogram. This kilogram will be cancelled with kilogram, so this is in meter square per second square. So therefore we can write this meter square per second square is joule per kg, joule per, because both are same. So W dot is equal to 3 kilogram per second, 244, this is 2443.94, this is 2443.94, 2443.94 kilojoule per kg minus 3214 kilojoule per kg, this is kg. Now here these values are kilo, so to convert this into kilo, divide by 10.3 and write here kilo. So meter square per second square is equal to joule per kg, and this is kilo, so kilojoule per kg. And if we simplify this value, so the answer will be 11.597 kilojoule per kg. Now W dot is equal to 3 kilogram per second, and to if we simplify this value, this is 758.5 kilojoule per kg. So W dot is equal to, this kg will be cancelled with kg, and kilojoule per second, joule per second is equal to watt. So 3 multiplied by minus 758.5 is equal to minus 2275.5, minus 2275.5 kilowatt. And negative sign mean it is a turbine work of expansion. Negative sign means this is power output. This is power output. Now this is work. This is simply, this is rate of flow of work. This is work output. Work output. Now we are finding power output. So efficiency, mechanical efficiency is equal to rate of flow of work divided by power output. Power output divided by W dot, rate of flow of work. So this implies that power output is equal to mechanical efficiency multiplied by W dot. So mechanical efficiency is 0.9 and W dot is minus 2275.3 kilowatt. So mechanical efficiency is equal to 2047.95 kilowatt, and if we round this will be equal to 2048 kilowatt. This is power output. Negative sign means that this is power output. Now change in entropy S2 minus S1 is equal to, S2 is given to us, is found by us, already we found S2 and S1. So S2 is equal to S2 is equal to 7.411 kilojoule per kilogram per Kelvin minus S1 is equal to 6.769 kilojoule per kilogram per Kelvin. So this S2 minus S1 is equal to 0.642 kilojoule per kilogram per Kelvin. And positive sign means that entropy increases. And one requirement is that show that the process is irreversible. So is the second law of thermodynamics show that for adiabatic process will be irreversible. Irreversible if entropy increases or remains constant. So as process as as entropy increases and process is adiabatic. So it is so hence the process is irreversible. Process is irreversible. So this is final result. We show that the process is irreversible. We find S2 minus S1 and power output. So for more problems, please like and subscribe my YouTube channel and share with your friends. Thank you.